This is a short video to explain some of the principles behind the use of the trapezium rule. At first sight, it may not be obvious why the equation across the screen here actually works. First of all, it's important to remember that the purpose of the trapezium rule is to try and calculate the area under a curve, and to do this by splitting up the curve, so if you like the representation being shown on the screen at the moment, splitting up the curve into a series of trapezium shapes or trapezoidal shapes, and then to calculate first of all the area of the first trapezium, then the second one, then the third one, the fourth one, the fifth one, and so on, and then add up all of the areas that you have to get the sum, so thereby giving the area under the curve. Okay, well, let's have a look and see why this equation that we have here actually works. Now, on the screen at the moment, we can see we've got a representation of the first trapezium in the sequence that we had on our original diagram. So the length of this side here, h0, and the length of this side here, h1, represents the variable on the vertical axis. Often this is force, but in other situations it might be velocity or something else. But let's consider for the moment that we are dealing with the force situation. So I've got the value of the force represented by h0 at the beginning of the time interval. I've got the value of the force represented by h1 at the end of the time interval. Now, if I find the average of those two values, so h0 plus h1 divided by 2, in essence what I'm doing is finding the height of this rectangle here. So we can kind of see that if we have a rectangle based on h0 plus h1 divided by 2, with t being the base, time base, then actually what we can calculate is this rectangle whereby whilst we miss this little bit here, we've also included this little bit here, and it should be fairly clear that these very closely approximate to the same areas. So simply multiplying the h0 plus h1 divided by 2 height, so that's this one illustrated on the screen, by the time, then I will get a very good approximation to the area of this part of the curve. Okay, so if we look at that in sort of equation form, this top equation here, h0 plus h1 divided by 2 multiplied by t, that will give us the area of that first rectangle. Now we could of course just multiply that out a little just to show that we could also have written that as h0 divided by 2 plus h1 divided by 2, again multiplied by t. Now if we did that for each of the trapeziums, then we would have a whole sequence of values as shown in the equation at the bottom here. So we have h0 over 2 plus h1 over 2, that represents the first trapezium. Then we'd have h1 over 2 plus h2 over 2, that would represent the second trapezium. We have h2 over 2 plus h3 over 2, that would represent the third trapezium, etc., etc., all the way up to the very last trapezium that we were interested in. And then because t, the time, would be common to every single calculation that we did for the area, then we could put that outside the brackets. Now if we look at this equation, we can actually see we can simplify it, because after the h0 divided by 2, we actually have h1 over 2 plus h1 over 2. In other words, half of h1, half of h1. So two halves would make a whole. And in the same way, h2 over 2 plus h2 over 2, again, that would make a whole. And then we could carry on that sequence all the way to the end. And if we did that, then we would end up with our original equation. So if we have a look back at our original equation, we can see it's only the very first term, h0, which is divided by 2, and the very last term, hn, which is divided by 2, and then in the middle we have all of the combined halves, which actually make, if you like, whole h1s, h2s, h3s, etc. Not forgetting at the end of the day that whatever we get for this summed value here, that we must multiply by t, which is the time base. Okay, this concludes this little video which explains how the trapezium rule actually works.